So in the beginning, we have studied how the non-aqueous solvents are classified into different classes. Our syllabus is restricted to the study of non-aqueous solvents such as liquid ammonia and liquid sulfur dioxide. The study as it is revealed with regard to liquid ammonia and liquid sulfur dioxide. Before going to start with the actual study, last time we have seen how these non-aqueous solvents can be conveniently classified into three main classes. The first class, as we know, is a protic and aprotic solvents. In this regard, we have seen that the classification that is based on the composition of the presence of H plus ions, whether a particular solvent that liberates or furnishes H plus ions during the course of a reaction is known as a protic solvent. That means protic solvents are those they can have at least one hydrogen atom which is capable of giving during the course of a reaction. So the word protic that stands for the liberation of H plus ions. In this same class, another type is known as a aprotic solvent, the definition of which is exactly refers to that of this protic solvent. A aprotic solvent is that substance which neither gives nor takes a proton or which neither give nor accept a proton. For example, CCl4, carbon tetrachloride, or benzene C6H6, or chloroform CHCl3. In all these chemicals, proton is present, but these are the solvents. They do not give nor accept any proton during the course of a reaction, hence are known as a aprotic solvent. The second class that is known as ionizing and non-ionizing solvents. The ionizing solvents, which are those they undergo atto-ionization. The word atto-ionization means when these solvents are involved in a chemical reaction, then these solvents they undergo atto-ionization. That means the self-ionization, they undergo self-ionization, that is known as a ionizing solvent. These solvents are polar in nature and have high value of dielectric constant and dipole moment. They are the good solvents for ionic type of solvent, for example, liquid HF, liquid ammonia, etc. Another class under the same category is known as a non-ionizing solvent. These are the solvents. They do not undergo atto-ionization, that means self-ionization, or attoprotolysis, that is furnishing of H plus ions during the course of a reaction is not done by these solvents and hence are known as a non-ionizing solvents. Now, this is a second class where these are known as the non-ionizing solvents. For example, again we shall take the example of CCl4, carbon tetrachloride, and second example is a C6H6, that is a benzene. These are the solvents which are regarded as a non-ionizing solvents because they do not undergo atto-ionization or attoprotolysis. They are not undergo a process of ionization, atto-ionization. That means they are unable to furnish H plus ions. Now the third category, that is known as a polar and non-polar solvents. What is this polar and non-polar solvents? The polar solvent is the solvent which is having two different poles, for example a positive pole and a negative pole. So these are the solvents are capable of atto-ionization. For example, I would like to give you Here the example of BrF3, bromine trifluoride. When bromine trifluoride is involved as a polar solvent, it easily undergoes BrF2 plus and BrF4 minus. Here, these are the solvents. They undergo autoionization. They are having two existence of two different poles. So here, if we compare the electronegativity values of bromine with that of fluorine, then fluorine is a highly electronegative, that is having the electronegativity value 4 units, as compared to bromine it is having 3.5. So they are highly reactive and are therefore difficult to handle. So it is very difficult to handle all these solvents during the course of a chemical reactions, and the reactions which are carried out in all of such solvents are of acid base type. That means they furnish or they undergo autoionization. The non-ionizing solvents are those, non-polar solvents are those, they do not have presence of two different poles. In all such solvents, autoionization of these solvents do not occur. Exactly reverse definition is exhibited by non-polar solvents, that they do not undergo autoionization, while the polar solvents they undergo autoionization. They have a donor atom like oxygen, sulfur, nitrogen in their molecules. For example, aceto nitrite, dimethyl sulfoxide, dimethyl formamide, tetrahydrofuran, that is known as the THF. All these are the examples of the non-polar solvents. So with regard to the classification of the solvents, we have seen the three different classes, namely the protic and aprotic. Then second is a ionizing and non-ionizing, and third is a polar and non-polar type of solvents. So different authors have suggested different types of classification, but the universally accepted classification that just now we have discussed, protic, aprotic, second is a ionizing, non-ionizing, and third is a polar and non-polar type of solvents. So you should bear in mind that these are the three main classes of the solvents with regard to the liquid sulfur dioxide and liquid ammonia. Now the today's talk that we are going to discuss about the leveling effect. What is this leveling effect that we have to study? For this, just see what is this leveling effect. Now the leveling effect that we are going to study, this is the leveling effect. Sometimes a question may be asked particularly on this leveling effect. Leveling, the word means to limit or to restrict, to limit or to restrict the ionization or proteolysis process. So leveling is nothing but it is a type of effect that is that controls or that governs the ionization, that is the autoionization of the solvents that just now I have referred as a liquid sulfur dioxide and liquid ammonia. I would like to exemplify this particular concept. The concept is very simple to understand. Let us take an example of the acid. For example, Ha is stands for acid. In a particular solvent, for example, liquid ammonia or liquid sulfur dioxide, these solvents they act as a base because they receive whatever protons that is liberated by acid during the course of a reaction. Here, if we see the chemical reaction that is taking place between an acid and a solvent, that is base, then they definitely form certain product or products. So we know that when we carry out a particular reaction, chemical reaction, Then acid, when it is added to any solvent, that definitely forms a product. So in equilibrium mixture, that is if we try to calculate the K equilibrium, then at equilibrium, the solution definitely contains certain amounts of the product and certain amounts of the reactants. So there is always equilibrium setup between the reactants as well as the products thus form. So if the value of this K, the value of K, if it is more, that indicates that this acid dissociates completely. That means 100% dissociation of acid takes place. This is nothing but when the value of K is more, that indicates that acid is completely dissociated, or full dissociation of this acid. That means this acid can furnish whatever H plus ions are there, those H plus ions react with the solvent so as to form the product. That means if the value of K is less, that indicates the dissociation of acid is less. So the value of K, that is the value of K that is obtained at equilibrium, if the value, if it is a low, then that indicates the acid can capable of furnishing only few H plus ions during the course of a reaction. So the strength of this acid, the strength of this acid, that is wholly governed or depend upon the solvent. So the dissociation of acid is entirely governed or controlled by solvent. What is the meaning of this? If this solvent is strong, then strong, under the influence of strong solvent, 100% dissociation of acid is there. That means the acid strength is, or strength of acid is strong. Now suppose the solvent that is used during the course of a reaction, if it is weak, so when a weak solvent is there and acid, when it reacts with such weak solvent, then the H plus ion, that is a auto ionization that takes place below 100%. That means there is no 100% dissociation. That means only few H plus ions are given or furnished by this acid. Under such circumstances, the acid is regarded as a weak. So indirectly we can conclude that the dissociation of the acid is completely governed by the base that is involved in a particular chemical reaction. So if the solvent is strong, then acid dissociates completely, and hence the strength of acid is strong. If the strength of, or the solvent thus used, if it is a weak, then acid can furnish only few H plus ions. That means the strength of acid is weak. That means this acid is weak. So the strength of acid during the course of a reaction, that is entirely limited, or it is governed, or it is restricted only because of the presence of solvent. So with regard to solvent, the strength of acid is determined. So from this one can define the leveling effect is that leveling effect is nothing but it is a property. It is a property due to which, it is a property of solvent. It is a property of solvent due to which acid strength, due to which acid strength of a acid is increased or it is decreased. This effect is known as leveling effect. This effect is known as a leveling effect. So what is a leveling effect? Leveling effect is nothing but it can be defined as it is a property of a solvent due to which the acid strength of an acid is increased or decreased, and this is known as a leveling effect. And we have seen this also. If the solvent is strong, acid strength is strong. If the solvent strength is weak, acid strength is weak. So it is a property of a solvent which governs or which limits or which restricts the ionization or the dissociation of acid. And depending upon how the acid dissociates, that means if 100% dissociation is there, the acid strength is strong. And if the dissociation of acid, if it is not 100%, then this is known as the weak acid. Now, I would like to give you one more example, that is the reaction of HCl in water. For example, HCl, as it is a strong acid, as we know, if HCl is added to water, then the H plus ion of acid combine with the H2 molecule, and it can form H3O plus Cl minus. So the dissociation of HCl in water is governed by this solvent. So this solvent, water, now acts as a base, as it is an acid. So the dissociation of hydrochloric acid is governed or controlled by water so as to form H3O plus. So H3O plus can sometimes also be written as H plus, which can be written as, this is oxygen, this is, these are the two hydrogen atoms. Oxygen is a negatively charged, and one more hydrogen is present, that is a positively charged. So this is known as a hydronium ion. So this is known as a hydronium ion, H3O plus. So here this is nothing but H3O plus. So there is greater attraction between this oxygen, that is a negatively charged species, with the hydrogen, and because of this the dissociation of hydrochloric acid is governed. So if we take another example, HClO4 or H2SO4 or HI, the ionization of these with, or the reaction of either of these acids are basically strong. So its reaction with water, either of these acids, when they react with water, the strength is decided by the solvent. So even though HClO4 hydrochloric acid, hydrogen chloride acid, and sulfuric acid and hydroiodic acid, the strength of which is governed or decided by the water molecule that act as a base, and all these are the acids. So this acid strength is wholly governed by water molecule, that is a solvent, and hence it is known as the property of this solvent which governs the strength of either of these acids. As we know, take for instance one more example. As we know, acetic acid, it is regarded as a weak acid, as we know, but when this acetic acid, it reacts in presence of liquid ammonia as a non-aqueous solvent. So this is a non-aqueous solvent which acts as a base. Here, in presence of non-aqueous solvents such as base, this hydrogen that is given up, or atto-ionization or attoprotolysis takes place, and hence it can form NH4 plus, and anionic species such as CH3COO minus, that is formed. So here this, in presence of a solvent, that is liquid ammonia, now this weak acid behaves as a strong acid, because the solvent, that is a liquid sulfur dioxide, sorry, liquid ammonia, in presence of this liquid ammonia, this weak acid undergo atto-ionization, and hence it can produce more and more H plus ions, and hence now acetic acid becomes a strong acid in presence of liquid ammonia. Basically, acetic acid is a weak acid. Why it is a weak acid? Because if we look at the ionization of acetic acid, it can furnish very lesser number of H plus ions during ionization. But if we carry out the reaction of acetic acid in presence of a solvent such as liquid ammonia, then acetic acid can furnish more and more H plus ions. Why it can furnish more and more H plus ions? Because this solvent decides whether this acid is a strong or weak, and this solvent forces acetic acids to furnish more and more H plus ions, and now in presence of ammonia this acetic acid becomes a strong acid. So in brief, the leveling effect is nothing but it is a property of a solvent due to which the acid strength of an acid is increased or decreased, and this is known as the leveling effect. That means indirectly the presence of solvent that governs the strength of acid or base during the course of a chemical reaction. So this is all about the leveling effect. We shall proceed further with the last part of this topic, that is known as the acid base reactions in liquid sulfur dioxide. We have seen similar type of reactions with that of liquid ammonia, where we have studied when two molecules of ammonia they unite together, then they can form the required product that we have seen during our last lecture, that in presence of two molecules of ammonia, when NH3 plus NH3 they react, they can form NH4 plus ion plus a amide ion. When this amide ion again reacts with ammonia, that can form imide, that is NH minus, and when these NH minus, that is imide, reacts with ammonia, it can form NH4 plus and N3 minus, that is a nitride. So the formation of amide, imide and nitride, that is NH2 minus, NH minus and N3 minus, these are known as ammono bases, and NH4 plus is known as ammono acids that we have studied last time. Now a similar type of reaction, those are taking place in presence of a sulfur dioxide as a non-aqueous solvent. Now on the basis of Lewis concept, the atto-ionization, on the basis of Lewis concept, the atto-ionization, the another word you should know, that is known as attoprotolysis. Atto means self, ionization that means when these solvents they undergo ionization, and protolysis means they can give their H plus ions during the reaction, that is known as attoprotolysis, that can be regarded as the acid base reactions in sulfur dioxide. Now suppose for example, if we take for instance two molecules of the solvent, that is liquid sulfur dioxide, then during the course of a reaction one of the hydroxygen that is given by the sulfur dioxide to this another molecule of sulfur dioxide. So this SO2 is regarded as acid 1, this SO2 is regarded as a base 2. This is a solvent, hence we regard this as a base. So when one of the oxygen that is given by this acid to this base, the final reaction is that SO2 plus one of the oxygen that is given, then becomes SO3 minus. So this is known as the thionyl ion, known as a thionyl ion, which is regarded as a acid 2, and SO3 minus, that is known as a sulfide. It is not sulfide, sulfide is a S2 minus, this is sulfide, and it is regarded as a base 1. So we have obtained a conjugate acids and bases, that is conjugate acid of SO2 is a conjugate base, that is sulfide, and for this base the conjugate acid is a thionyl ion. So when this SO2 gives its one of the oxygen, it can form SO3 2 minus, and remaining part is a SO2 plus, that is known as a thionyl ion. So in this case, the reactions which are occurring with two molecules of sulfur dioxide are again known as a acid base reaction. According to Levy's concept, an acid is nothing but which can furnish the ions during the course of a chemical reaction. If we want to show this particular reaction, then we can also show the reaction, that is SOSCN2 minus. This is known as an acid, that is known as thionyl thiocyanate. This is known as a thionyl thiocyanate. Its reaction with K2SO3, that is a potassium sulfite. Potassium sulfide. If we carry out this particular reaction, then this reaction gives twice KSCN, that is a potassium thiocyanate, plus two molecules of sulfur dioxide that is obtained, that is this is known as a salt. So this is a reaction that is taking place in sulfur dioxide. Sometimes another reaction that can be shown, that is some amphoteric type of behavior, that is also shown by zinc plus 2 salts. For example, what is the zinc plus 2 salts? For example, if we consider zinc chloride, it's a reaction with potassium sulfide that in presence of liquid sulfur dioxide. This reaction also takes place in presence of liquid sulfur dioxide. Here this can form zinc sulfite ZnSO3, and two molecules of potassium chloride are obtained. Here this is zinc sulfite. When it forms ZnSO4, that is known as a zinc sulfate, but here that forms a zinc sulfite. So this zinc sulfite ZnSO3 in presence of potassium sulfite, in presence of a solvents such as sulfur dioxide, it can form K2ZnSO3 twice. So this is known as a potassium salt of zinc sulfide. So the amphoteric type of behavior that is shown by this sulfur dioxide. So liquid sulfur dioxide, on the basis of this Levy's concept, it can be regarded as it undergoes autoionization, and hence it can give certain acid base type of reactions during the course of this reaction. Hence the thionyl ions which I have shown here, these are the thionyl ions which are shown here. These thionyl ions act as a acid, while sulfide ion act as a base. These are the sulfide ion that act as a base in presence of liquid sulfur dioxide. Thus, the substances which dissociate to produce thionyl ion, that is SO2 plus, behave as an acid, whereas those which dissociate to produce sulfide ion, that is SO3 2 minus, behave as a base in presence of sulfur dioxide. Hence this is known as the acid base reactions. Those are taking place in liquid sulfur dioxide. So we shall again